Good morning, everyone. It's our honor and privilege to welcome you all for the E-Faculty Development Program on Advanced Material and Manufacturing System organized by Mechanical Engineering Department of Christian College of Engineering and Technology, Bhilai. Today we have Dr. Rahul S. Mulik with us. Welcome you, sir, in this today's session. He will deliver a lecture on machining of quartz by ECSM process. I would like to take this opportunity to introduce our today's speaker, Dr. Rahul S. Mulik. He is Associate Professor in Department of Mechanical and Industrial Engineering at IIT Roorkee. His area of interest are conventional and non-conventional machining processes, finishing processes, micro machining, FSC, and welding, MMC, and rapid prototyping. He has a total vast experience of 15 years in teaching and industry. He has also worked in Kirloskar Brothers Limited, Sangli. He got Binani Gold Medal Award for his best paper from Indian Institute of Metal, Kolkata. One of his students got OVD Fellowship by University of Alberta, Canada for his PhD work. He has completed his Bachelor of
I think it's buffering, I believe. Radhiji?
Institute of Technology, Allahabad.
Sorry, over. Oh, cut it. Hello, Gajgar sir, is it over?
Radhiji, you are not audible. Shall I start?
Sorry,
Yes, sir. Please, you can start, sir.
Sir, 1 minute, 1 minute. Just.
Okay.
He also published about 14 research papers in national and international journals, and also attended number of conferences at international and national level. He got patent for device for ultrasonic assisted magnetic abrasive finishing process and process thereof. So this was the brief introduction of Dr. Rahul S. Mulik. So now I will request to Dr. Mulik, please continue today's session, sir. Please, sir.
Namaskar to everyone. I'm very much thankful to Radhaji for this nice introduction, and it refreshes my association along with Dr. Radhaji long back. We did our master's degree at MNNIT Prayagraj long back together. So
Thank you, sir.
I cherish those memories with him. So today I start with topic micro machining of quartz material with electrochemical spark machining process. Am I audible to everyone?
Yes, yes, yes.
So these are contents of my presentation. We'll start with the introduction, then the working mechanism of the process, then a certain literature review, then application of the setup, and studying the various process parameter effect on the material removal rate. So first we'll start with the introduction part. I know this figure shows various tools related to our conventional machining. Generally machining, what we do, we produced finished product converting raw material into the finished product through various processes. So we start with the foundry, then machine shop, then the assembly, testing, and final dispatch to the market. So in earlier days, the conventional tools were used, and the elementary metals such as iron, bronze were used. Shaping this material is even today it's very easy. Even at that time, it was easy with available technology. But as the technology advanced, new materials were being introduced, and sometimes these materials they are very difficult to machine, even too difficult to process. So, in order to machine or in order to shape these difficult to machine materials, various techniques were employed, and these techniques generally introduce different type of sources of energy. That's why they are known as the non-traditional machining sources. For example, it's monsoon season and you can see so many discharges in and around, electric discharges. Same discharges, they are produced artificially and they are concentrated in a particular zone and machining is done. Sometimes a chemical energy is being used, if you are well aware with the etching process. So that is common source of a chemical based machining process. Then we have electrochemical reaction. With the help of electrochemical reaction, we can remove the material. So this is not a conventional thing. So these techniques, they are known as a non-conventional or non-traditional machining processes. Some of the process they are commercialized. Even now they are we have Indian manufacturers. Some machines are being exported to various countries, even to developed countries. So this much advancement is there. Even Indian manufacturers, and hereafter, as our Prime Minister Modi ji is giving thrust on this Make in India, so many manufacturers are coming up. They are discussing with various IITs for this technology. The purpose of this lecture is to make aware you people regarding various technologies and how to produce this technology at your institute in a cost-effective manner. Because some laser-based technologies, they are very expensive because that equipment is itself expensive, laser-based, plasma-based, or all these things. This table shows various non-traditional machining processes along with their mechanism and energy source. So for example, we have energy as a mechanical. Then the basic mechanical will be erosion, and we have pneumatic or hydraulic. Typical processes are abrasive jet machining, ultrasonic machining, and water jet machining. In abrasive jet machining, the flow of abrasives, for example, this is my workpiece. Flow of abrasives is impinged on the workpiece to get a certain dimension. So in previous figure, if you look at the figure, second from the left, you can see the ultrasonic machining. Here, this abrasive slurry is being impinged and tool is being vibrated. So these abrasive particles, they strike against the workpiece, they erode the workpiece material in a smaller quantity. Even this water jet machining, water jet is impinged on the workpiece and it is used to cut the steel workpieces as well. This much tremendous power is there, the water itself. Then we have a source electrochemical energy. The mechanism is ion displacement. As you are aware with the Faraday's law, that supply voltage is directly proportional to material removal. That's fundamental. So material is displaced by ion. So transfer media is electrolyte. Commonly used processes electrochemical machining and electrochemical grinding. Then we have a chemical energy. The mechanism is ablative action, and energy source is corrosive agent. Chemical machining or basically etching is the best example of this process. Then we have another watching this sci-fi movies of Hollywood. Like there are several series available. Star Wars or everything. So in that you can see some align, they are coming to Earth They have certain gun, to trigger the gun, some rays they are coming out and they are striking against a human being and human vaporizes. So that is basically a plasma or chain of ions. So that is basically ion beam machining or plasma arc machining. These equipments, they are costly, but that is only in sci-fi movie. In actual, commercially, these machines are available. They are expensive. Everything is done in controlled atmosphere. So in case like a flow of electrons, then we use high voltage, that is electro discharge machining, laser beam machining, and plasma arc machining. So basically, thermal erosion is the mechanism for this processes. So what happens? Arc strike against the workpiece, material is vaporized and evaporated. So electro discharge machining is very popular, and these machines are commercially available. Now, so many machines are being exported to various countries from India. So if you look at this table again, these are processes. So every process has its own advantage and own limitations. So like water jet machining, you cannot use everywhere. If you want to drill a micro hole, that's not possible. So again, abrasive jet, you are using the abrasives passing through certain nozzles. Like if you look at this figure, again figure 2, so abrasive slurry passing through certain nozzle, that abrasives, they start eroding the nozzle as well. So performance is affected. So if you look at the ECM and the EDM processes, we need material to be electrically conducting. So in case if material is not electrically conducting, especially certain ceramics, it is really difficult to machine them. So what we do, we sometimes we combine minimum 2 or more non-traditional machining processes, give birth to a new hybrid machining process. So that the limitation of both the processes can combine together, take the advantage of this limitation. So in this group, I won't discuss other processes, but main thrust will be based on the electrochemical machining combination of electrochemical machining process and electro discharge machining process. So when these two processes, they are very popular in the industry. Commercially, they are available. The major limitation is workpiece. This is my workpiece. This is my tool. So workpiece has to be electrically conducting. Otherwise, electrical circuit is not completed and no material removed. So in order to machine electrically non-conducting material, we combine ECM and EDM, give birth to new process known as electrochemical discharge machining or electrochemical spark machining process. So in this process, the workpiece is not essentially part of any electrical circuit. That we are going to discuss in forthcoming slides. So this figure shows a certain classification of hybrid machining processes. Even what you can do at your institute, you can combine various processes and you can produce your own hybrid machining processes. That's why I don't suggest laser based, because they are very expensive. And see, EDM and ECM, they are not, of course, EDM machine is expensive, but you can locally do it with very few lakhs of investment. Of course, your institute may sponsor that, or you can collaborate with the local industries where they are getting difficulty in machining these kind of materials. So like grinding is a conventional process, you can combine with this electrochemical process. This will become electrochemical grinding process. Same with EDG. And even you can combine grinding, ECM and EDM, you will get electrochemical discharge grinding or electrochemical discharge machining. Then you have ultrasonic machining, you can combine with various processes and you can give birth to any hybrid machining process. It's up to you. You have to find out the problem and accordingly you need to design a setup. So many processes, so I don't prefer LBM best because these are very expensive and it has very limited usage. So it is electrochemical spark machining process is a spark assisted micro machining process. Of course, it is a micro machining process as compared to conventional machining. There you can see a lot of debris, but in these micro machining processes, sometimes debris to find the debris is very difficult. So these are micro machining processes, and it combines ECM and ADM. Main material removal is because of ADM phase only. That also we are going to discuss. So this figure shows the schematic of any ECSM setup. Here you can see a counter electrode or a positive electrode anode is there. Then we have a cathode electrode or tool electrode. Workpiece is kept in the vicinity of a tool electrode. Workpieces are not part of any electrical circuit. The entire setup has to be kept in electrolyte. Then you apply voltage. Current will be drawn in order to complete the circuit, and the mechanism that we are going to discuss in the next slide. So hope this schematic is very clear. This kind of setup is easy to develop. This setup doesn't involve that much cost. Even this setup can be developed for your PhD work or some BTech or master's project as well. And this will long last. Even commercial applications are possible. These are actual photographs, not from my work. This taken reference from certain other work. Like you can see, one big electrode is there, small electrode is there. You can see once supply voltage is started, bubbles are generated due to certain electrochemical reaction. Here you can see if we are using acidic medium, these are the reactions, how hydrogen bubbles they are formed. When in alkaline solution, hydrogen bubbles they are formed. These bubbles you can see here, they are hydrogen bubbles generated at tool electrode. So these are a certain chemical reaction. No need to remember or commit to memory these reactions, just to understand how these reactions they are taking place in different medium. So your electrolyte may be acidic or the alkaline, depending on the situation. Acidic is more corrosive in nature, so that's why sometimes we prefer the alkaline solution. Where you want to corrode the material or remove the material at a faster rate, there you can prefer acidic medium, but generally we prefer alkaline solution. So once we increase the supply voltage, current is drawn here, electrochemical reaction is taking place. You can see so many bubbles, and so as you go on increasing the supply voltage, more will be the electrolysis of the electrolyte. In figure B, the second figure on the right side, top right side, you can see so many bubbles they are formed. These hydrogen bubbles, they form a thick blanket on the electrode. This is my electrode. A thick cover is formed. Figure C, you can see the cover is thickened. What happens? These hydrogen bubbles, they are dielectric in nature. So since electric current, the electric circuit is not completed, what happens? The tool electrode, the current tries to jump. It tries to reach the electrolyte to complete the circuit between tool electrode and another electrode. But now my electrode is covered with the hydrogen bubbles. Hydrogen bubbles, they are being dielectric in nature. So here, electrode discharge machining phase starts. So since the electrode is covered, the thick cover of hydrogen bubbles, there is a constriction to flow of current. So what is flow of current? Basically flow of electrons. So the electrons present at this end of electrode, they try to jump. So they collide with the hydrogen bubbles, hydrogen molecules, further liberating electrons, atoms, protons, neutrons, and this continues till circuit is complete. So in last figure, you can see the circuit is completed in form of spark. This is instantaneous generation of a spark, and workpiece is kept in the close vicinity of the spark, and there will be striking of arc or spark against the workpiece. There will be melting, localized melting, then vaporization, and again this process continues till we achieve a desired dimensions. So this is the general material removal mechanism in ECSM or ECDM process. Any doubt in this slide? Please feel free to ask. So this is all about chemical. This schematic shows like how this bubbles are generated. They are covering the entire electrode. Formation of gas film is there. Then melting, vaporization. That is the main mechanism behind the material removal. So we have like a bulk region where bubbles are formed. Then jumping bubbles, they can jump on either side, and adherence region where the hydrogen bubbles, they stick to the electrode. So this is like a conventional mechanism, let's say a drilling or creating certain channels. Then, for example, I have like this PCB, printed circuit board, or any other circuits of, let's say, different material. I need to cover the micro channels or the micro slits like this. So this drilling kind of setup is not suitable. Then we go for another setup known as a traveling wire electrochemical spark machining process. To develop this setup is like a typical. Very few attempts are available if you even you go for a literature review. So this is very typical setup, but fortunately we could develop this working setup. Even today it's working. So one of my PhD student, he developed this. So many MTechs worked on this. So what we used is traveling wire. One is donor pulley, another is receiving pulley. So this electrode is moving continuously. That's why it is known as a traveling wire electrochemical spark machining process. This schematic of the traveling wire process that we are going to discuss in detail. So this ECSM process has a potential to machine non-conducting materials such as alumina, quartz, certain ceramics, or certain composites. So microfabrication of miniature machine tools for micro machining is also possible. Then micro slitting operation of ceramic components is possible, and even improving machining of 3D microstructure is also possible. There are certain limitations, like beyond particular electrolyte temperature, performance start deteriorating because it's a continuous overheating of the electrode and electrolyte. So electrolyte temperature rises. So both machining time and hole entrance diameter. Sometimes hole entrance diameter we call as the enlargement of the hole. That also we are going to discuss why this is happening. Then low material removal rate is again a problem, and pure surface finish. So basically this is thermal erosion process. EDM or any thermal discharge goes best process like a plasma or laser. That thermal erosion process, you don't expect any surface finish in that. I mean, good surface finish. It's not a finishing process. Try to understand. Finishing process, they are altogether different. So if anybody is saying that I can achieve good surface finish with EDM, that person is lying, or that person is not having any basic understanding of the process. This thermal, certain surface roughness will be there that you cannot avoid. So high overcuts occurs due to side sparking. What is that? That also we are going to discuss. I will skip this literature review. Like if you look at this figure again, yeah, you can see in the last figure there is a lot of sparking. This sparking phenomenon is random. Unfortunately, I don't have board and other kind of things, but I will show one figure. Like any surface, if you observe, yeah, any surface if you observe under microscope, there are peaks and valleys. If these peaks and valleys dimensions are more, let's say this is mean line, and these are peaks and valleys. If these peaks and valleys they are more in length, surface will be rough. And what happens every time this peak is changing, so sparking will take place at a minimum resistance. So every time these peaks and valleys they keep changing, and sparking will be there. So sparking is a random phenomenon. We don't have as such control on the sparking. So sometimes if sparking is not controlled properly with the help of a combination of process parameters like input voltage and electrolyte concentration, then sparking will be erratic, and it will what happens, for example, I want to produce a circular hole won't be produced So this is expectation, but because of this random phenomena, this kind of structure will be produced. So this is overcut or something like uh, entrance diameter becomes bigger. This reason of this erratic sparking. Again, sparking is difficult to control, but we need to control it with a certain process. So literature review like ECSM was first developed in the Japan, and then it propagated. Even for this process today, we don't have any commercial machines available. Depending on the requirement, we are developing the setup. So I won't go into the details of this literature review, but if you look at the last line, so if you look at the last line and the third column workpiece material, this difficult to machine materials being used. Like in our case, we used quartz. And if you look at the diameter of the wire, for the first time, we introduced 0.1 mm, or let's say 100 micron diameter wire successfully. I mean, first time we used this in ECSM process. So if you look at the various material removal rate, it is few milligram per minute. Then surface roughness is typically rough. We'll discuss about the application of the setup. We have three kinds of system: mechanical system, electrical power supply unit, and electrolyte supply unit. This is a schematic of our setup. Here you can see, of course, we used mechatronics in this in order to control the feed motion. Like a relative feed is nothing but a relative motion of tool with respect to workpiece. So in case a tool is our wire, traveling wire, you have donor pulley, you have receiver pulley, and this motion controllers are there. Then we have DC power source. The main thing expensive is DC power source. Even these DC power sources, they are commercially available. As per your need, you can get it fabricated. So something from 5,000 to 1 lakh kind of thing, they are available, but this can be used in so many applications. Like machining chamber was made up of a Perpex, so Perpex is not that much expensive. It is available everywhere. Brass wire is also available everywhere. Motion controllers, they are also available in India. Sometimes now Make in India also available. So I mean, fabrication of this setup is not that much difficult. You can see the magnet that we are going to discuss. What is the use of magnet? Again, this magnet is permanent magnet, hardly 50 to 100 rupees. So what we tried, and this project was sponsored by our Department of Science and Technology, and we successfully implemented the technology for the first time using magnet in the traveling wire electrical spark machining. So setup is very easy. These are actual photographs, the setup. You can see the entire setup except this DC power source or DC power supply. Rest of the things, they are not that much expensive. Even computer are small. This computer used was P4 processor. Our department scrapped it and we used it. So a small software is there. That's not an issue. That is free software in order to control the entire motion controllers and everything. And this motion controllers, they are available in very few thousand rupees. So that's not a big deal to develop a setup, but you need a lot of innovation, you need to use a lot of brain. I mean, hard work is necessary to develop this setup. It took nearly 1 year to develop this setup. So in this process, first time we used a magnet. Now the reason, as I told you, the erratic sparking. So erratic sparking has to be controlled, and tried our best to control the erratic sparking with the help of permanent magnet. Now what happens, if you look at the basic process physics of the process or the basic magnetic fundamentals, so what we did, so once sparking is taking place, that is basically electrical phenomena. What we did, we introduced the magnet in the electrical field. So when we use magnetic field in the electrical field, Lorentz forces, they are acting upon the charge carriers. So if you look at the rule of thumb, so one effective magnetic force is produced which acts on the charged particles, and that is known as Lorentz force. So as I mentioned in the limitation, it has a limitation of lower material removal rate. So why this happens? When sparking is there, as you go deep into the workpiece, the flow of electrolyte in that small area is not that much effective. So sparking will be more erratic, and sometimes there won't be any sparking because of fresh electrolyte supply is not possible. Debris is more. So in order to flush out that debris and to have fresh supply of electrolyte, we have introduced the magnetic field, and Lorentz forces that are induced on that particles, and there will be fast removal. This schematic shows, like my workpiece is there, magnet I have placed. Again, I have south pole and north pole magnetic field lines. They are shown. How they are taking place in a machining zone, that is also shown. So you can see these magnetic lines. They are acting. They are inducing the Lorentz forces on the charged particles, and this continuous movement is there. So this movement you can compare it to the whirling action. So you have fresh supply of electrolyte continuously, and that is small gap. Like this is another schematic, and when there is no magnetic field, bubbles are generated. In the figure, the figure is actual figure of our setup. You can see the bubble generation. So in presence of magnetic field, when magnet is facing its north pole towards the workpiece, you can see the schematic bubble generation. Here you can see the bubble movement. I hope that figure is visible to everyone, and wire movement is also there. So basically in this mechanism, wire movement and bubble movement in the same direction. If you look at the next figure, when magnet is facing the south pole, bubble movement is opposite to brass wire. When we started experimentation initially, we're not aware about this phenomenon. Of course, it's research only. So what happened when we faced magnet south pole of a magnet towards the workpiece, bubble movement and wire movement were in opposite direction, and performance deteriorated. I mean, the desired results were not achieved. We were also shocked why this happened. Our hypothesis went wrong. What happened? Then we tried so many options, but then we went to the basic. We studied it again, the Lorentz forces. Then we changed the position of a magnet. Now north pole of the magnet is facing towards the workpiece. Now bubble direction and wire movement, they are in the same direction. So what happening? Bubbles, they're carrying out the entire debris, and fresh supply of electrolyte was possible. In this direction, bubble movement and wire movement, they're opposite, and that was hindering the removal of debris from that small domain. So that's why we need to do a lot of research. We need to do a lot of reading. This magnetic field is not our domain. Mechanical engineers, this is not our domain, but we need to study so many things together. So finally, we did a lot of experimentation. We checked the things and selected the north pole facing to the workpiece. So quartz was used, and because this is commonly used material in the piezoelectric applications such as transducers or any other electrical applications, but the machining of quartz is really difficult in a micro domain. These are certain material properties of the quartz. So I will not go into the detail, but you can see the tensile strength and hardness is tremendous. So after initial experimentation, we could find the range of so many process parameters, like voltage was kept between 24 to 36 volt, and wire speed was this, concentration of electrolyte, then inter-electrode space, like distance between two electrodes, then type of electrolyte was sodium hydroxide, wire diameter was kept constant 0.1 mm, and workpiece movement was also kept constant. So these parameters, they are identified after initial experimentation. Our main thrust was to find out material removal rate and to check the surface finish or surface roughness. So, I mean, we did the experimentation twice without application of field, normal traveling wire ECSM process, and with the application of magnetic field as well. The performance has to be compared. So, MRR improvement ratio with respect to non-magnetic field and with magnetic field was compared. So depending on the various process parameters, if you look at this table, there are various like voltage, wire feed rate, distance between two electrodes and electrolyte concentration. So based on various process parameter, the performance of normal ECSM and with the help of magnetic ECSM has been compared here. You can see MRR improvement was from, say, let's say 10% to 200%, depending on the process parameter. That's what, and you need to find out the optimum range of process parameter based on so many experimentation, and then you have to give the best. So, depending on the combination of process parameter, this is like one can easily say that higher wire feed rate is not desired, although voltage is higher, but the performance was very poor. So at the minimum value of wire feed, we are getting a good response. Then see, once setup is finalized, setup is ready for experimentation, we need to compare now the outcome of the process on various process parameters, like with the help of a wire feed rate. Like in earlier figure, you can see the lower the wire feed rate, higher is but again it tells the combination of various process parameter. So not a single process parameter is responsible. It's basically combination of various process parameters as possible. Like here you can see, as voltage is being increased, we're getting the higher MRR up to certain level. I mean, this comparison figure A is no magnetic field, figure B is with magnetic field. You can see the drastic difference between the material removal rate. Like this schematic shows the electrolyte jet formation, as it is clearly visible. If you look at this figure, yeah, the jet is clearly visible. In case of no magnetic field, jet is not there, bubbles are concentrating in that domain only. In this jet, some unwanted bubbles, they are being removed and debris also taken away. So this is explained with the schematic. Without magnetic field, you can see debris, they are lying here and there. When workpiece is facing magnetic field, debris is removed along with the wire feed direction. The jet is visible. Figure C shows magnetic field, workpiece facing south magnetic field, electrolyte jet and wire field rate, they are opposite, so that basically hinders the material removal rate. I think this figure, this schematic makes it very clear. These are actual figures, photographs taken during the machining. So without magnetic field, no jet. If magnetic field is applied, there is jet. Even for north and south, we have basically both the jets. Figure D, without magnetic field, sparking is shown. For all condition, sparking is being shown at various process parameters. But if you look at the top figures, like figure B and C, a jet is clearly visible. So this figure shows the discharge current. See, current is drawn. Current is dependent on the supply voltage. If no voltage, no current will be drawn in that area, and no sparking will be there. So we haven't considered current as a process parameter because current depends on the voltage. We need to study the effect of independent process parameters. Otherwise, it's really difficult to conclude something. So here you can see when we are not using any magnetic field, current drawn in that narrow range is high as compared to current drawn with the help of magnetic. See, this helps in reducing the wire cut mechanism. If current is drawn more heat will be generated, and that makes the wire and process stops. Because this is another problem in so many EDM based processes, wire breaks in between, and that leaves a scratch mark or chatter mark on the workpiece. That is not desired. The workpiece is scrapped eventually. So what we did, to develop the process. So with this, wire breakage was a bare minimum, and no chatter marks or no spark marks were on the workpiece. We used the oscilloscope to measure the current and the discharge zone or the sparking zone. The figures on the left, they show current drawn during sparking without a magnetic field, and figures on the right, they show sparks drawn when magnetic field was applied. If you look at the figures on the left, the peaks, you can see the sparking current, they are very erratic and random as compared to figures on the right. If you look at the figures on the right, peak current is small as compared to peak current without magnetic field, and somewhat uniformly distributed, somewhat. Not as I told you, sparking is a random phenomenon, and it's really difficult to control it. But still, with the help of a magnetic field, we tried our level best to control it. See, the current is also drawn less, 1 point at same process parameter, like voltage, input voltage remains same, but the current drawn is less in case of magnetic field. This increases the tool life as well, that wire life, and that cutting of wire comes down drastically. Further, we compared the slots produced by both the processes. Again, figure on the left without magnetic field, figure on the right, there are slots or holes produced with the help of magnetic field. If you look at the figures on the left, you can see the slit produced is not a uniform as compared to slit produced with the help of magnetic field. I'm again telling you, in any thermal illusion process, you cannot expect surface finish. What we did with the help of our hypothesis was, with the help of a magnetic field, we have stirring action in the sparking zone, so that we have continuous fresh supply of electrolyte, so that erratic sparking comes down drastically, and surface finish improves little bit. In our study, we could improve surface finish by almost 25%. That is also a good achievement. But if you look at the figure, the correctness, or let's say out of roundness or out of tolerances parts, they are produced very less. Like here you can see the white layer is typical phenomena observed in the any thermal erosion process. White layer is nothing but recast layer. Like, see, my arc is striking against the workpiece. Not all energy is passing into the workpiece. Some energy goes surrounding to electrolyte. Arc is striking against the workpiece. Material melts. It vaporizes. Not all material vaporizes. Some material again redeposited on the base material. So this redeposited or recast layer is known as a white layer. It induces the thermal stresses in the workpiece in that domain. Hope you are well aware with the welding processes, so how thermal stresses they are induced in that. And this decreases the life of the component. So with the help of magnetic field, we could minimize the heat affected zone, or known as a HAZ, or we could minimize the recast layer. The figures on the left, you can see a lot of recast layer is there, and on the right you can find the less recast layer. So as I told you, I mean, no one can claim that you can achieve excellent surface finish in thermal erosion process. That's not possible. Let me tell you frankly, this limitation will be there and you cannot overcome this limitation. You can minimize the limitation, but you cannot overcome it. So this is all about my small work. Of course, there are so many things to share, but the time limitation, I cannot share all the things with you. It will be a little boring. So this is all about my work. Now, I expect questions or doubts from the audience.
Hello. Please, participants, if you want to ask any question, you can put your question in the chat box or you can directly ask. Sir, there is one question. Will it be viable to make a BTech final year project from this topic?
Yeah, like I told you, DC power source is little bit expensive depending on the requirement. It can be between somewhere 10,000 to 1 lakh. What you can do, you can go for a lower voltage DC power source, so cost will come down.
हेलो
Yes, please.
हाँ सर, ये मैं ये जानना चाहता हूँ कि इस फील्ड में अभी क्या है, रिसर्च के क्या क्या है सर, किस टॉपिक पे अपन क्या रिसर्च स्टार्ट कर सकते हैं इसमें?
बहुत कुछ है भाई साहब, थोड़ा लिटरेचर रिव्यू देख लीजिए, मेरे पेपर नेट पे देख लीजिए, इसमें बहुत काम है। जैसे हमने क्वार्ट्स पे किया है, लाइक यू हैव अदर मटेरियल्स एज वेल, लाइक स्पेशली मशीनिंग ऑफ कंपोजिट becomes difficult by conventional method even today. There you can use this process, producing holes, micro holes. Like if you deep drilling is not possible with this process, there are limitations. You can overcome that limitation. We tried a small experiment on that also. We got good success in that also.
Okay, sir.
Any other question? Anybody want to ask? Hello. Sir, in this technique, the surface finishing is not good. So there are other any ways by which we can increase the surface finishing.
Like sometimes we prefer ultrasonic machining, but again producing this kind of depth is not possible in ultrasonic machining, or slits cannot be produced. So this is one of the best process available. Again, here what we can do, I haven't used electromagnet. One can use electromagnet to control the magnetic flux density in that domain. That's possible. Here we used permanent magnet only. Again, that is area of research.
Yes, participants. Any other questions? Okay, sir.
Okay.
No more questions.
Am I done here?
Yeah. On behalf of Department of Mechanical Engineering, Christian College of Engineering and Technology, I would like to express my gratitude towards Dr. Rahul S. Mulik for sparing his valuable time with us and sharing his knowledge with us. This topic was very interesting, and you have shared your knowledge, which is very useful for us also. And there are a lot of scope in the research. So research scholar also can take the advantages from this lecture. Also, I'm thankful to our management, our principal madam, for supporting, for giving all the support and providing the guidance for arranging this FDP. I'm also thankful to all the participants for participating in this FDP. I'm also thankful to our HOD sir for uh, guiding and supporting and organizing all these events. So thank you all again. Thank you very much, sir.
Okay,
Thank you, sir.
thank you. Thanks a lot for this opportunity. Okay,
Okay.
shall I leave?
Yeah, sir. Thank,
Okay.
thank you.
Hello. Gajgar sir. Hello. हो गए सर.